Good evening, students. I'll start with the class. In the previous class, we had seen the working of the engine and the refrigerator and the heat pump. Now the final one, that is the Carnot's engine. Before that, I had given you as the second law of thermodynamics. So those proper statements I'll give you. Second law of thermodynamics. Explanation point of view, I told you, not the entire heat can be converted back into work. I told them all the work can be converted into heat, but not all the heat which can be converted into work. So the actual statements, there are two people who gave this. One is Kelvin. So Kelvin statement. This is based on, see, told you there was a source, then there was an engine, and then there was maybe sink or reservoir 1, reservoir 2, hot reservoir, cold reservoir. We had seen that we were giving Q1 as the heat to the engine. We are supplying some heat from the fuel. Suppose some petrol is creating some heat energy which is given to the engine. Now as per this engine should be have been a perfect one which gives the entire Q1 into work. Okay, but the means converts into work, and this shouldn't have been there for an ideal one. The entire heat should be converted to work, but that doesn't happen. Some heat is always lost to the sink. This condition will never be possible. So as per that, the Kelvin statement, okay, Kelvin planks you can say. Actually not needed also, even if Kelvin also, otherwise say the Kelvin statement also. He said that no process is possible. This is like a process only. No process is possible whose sole result, means total result or alone result, is the absorption of heat from a reservoir. In the complete conversion of heat into work. It is not possible to convert the entire heat into work. It is not possible. Some heat is always lost. It is not possible to absorb the entire heat from here and give it to someone else. Some will be 100% lost. Something or the other, even minute level of heat will always be lost. Another fellow is a clauses statement. Same thing it means. Only thing this fellow referred it as a reservoir. The other one is saying from the reverse process, from colder to the hotter object. Wait, I'll write this and then explain. No process is possible whose sole result is the transfer of heat from a colder object to a hotter object. This is with reference to the refrigerator. So you can refer the refrigerator diagram. This is normal engine diagram which I had drawn. Refrigerator I have drawn ulta. This is colder and from there it goes to the hotter one, the outside environment. So this fellow is for this process. So it is not possible that the entire, we had seen that from refrigerator this was cold. Then over here something extra also was needed. It was not sufficient. Only this was not sufficient to give. There was work needed here. It is not possible to give only this much entire thing to here. No process is possible whose sole result is the transfer of heat from the colder object to the hotter object. Transfer of heat always takes place from higher temperature to the lower temperature. We know that if there is 50 degree and this is 30, obviously from 30 it will not go to 50. Then something that is called as reversible and irreversible processes. From the word itself, it's understood reversible means whatever is happening in forward direction can also work in the reverse process. If both the ways it is possible, then it is called as a reversible process. Any process which can be made to reverse, made to, you can say, made proceed in the reverse direction. All changes occurring in forward process are same as or are exactly reversed in the reverse process. Suppose if volume is changing from V1 to V2 in the forward, then if you are reversing the process, it should change again back to the same one which we had started from. Any changes occurring in the forward process should work back when you change the process. No heat, nothing should be lost to the environment. Everything exactly where you started. If you come back to the same point, then it is called as a reversible process. And irreversible is obviously which doesn't work, opposite of this. irreversible process. Any process, same thing you write, which cannot be made. Instead of can, it is cannot. Irreversible, I had given you many examples also. Like once you keep two gases, A, B, if they are separated, once you remove this bond, they will all mix up. But when you put that middle, this again the gases will not separate by its own. There are certain processes which cannot be reversed. So like mixing of gases, so that can be the example. These reversible processes are very rare. They work only in the ideal state. So that we'll see next now. That is called as the Carnot's engine. There was a person called Carnot. He tried to frame one engine that is only theoretical, or it is also called as hypothetical. Means it works only in theory. In practical life, such perfect engine will not exist. What he tried to say is that engine is the most efficient engine because it almost gave 100% efficiency compared to any other engine. He said that whatever engine he has designed is the most efficient engine. He also said it is reversible engine, although extremely difficult to attain that. Why does he say all this? Because everything he assumed. Okay, this is all about theory. He's just assuming if we take like this, if we take this type of piston, if we take this, it will work out. But practically, not. It's mostly hypothetical, means imaginary. So what all he assumed, he tried to take. So what he did is he took a piston, this a block which is covered, had some piston on it. So many things he assumed. This he assumed to be a frictionless piston. This he assumed to be ideal gas, which usually doesn't exist. Perfect ideal gas, very difficult. Then again he assumed whatever is this is perfectly conducting. Okay, so all the things whichever he was trying to assume, he was trying to consider them all perfect. Frictionless piston, in like any object without zero friction. Some friction will be there only. Whenever the piston is moving, friction means some roughness on the this. No, this can be 100% smooth. Okay, but he is assuming that this piston is frictionless piston. There is nothing, zero contact, like zero friction between the cylinder and the piston. Again, ideal gas also is assuming, and then this is perfectly conducting, means whatever heat you are giving to this base will go inside, not even a slide, it will keep it with itself or lost in the material. So all these assumptions is doing. So there are certain steps, okay, for a Carnot cycle. So I'll just show how it looks like, something like this. So we'll try to study what is this Carnot cycle. For that, we have to know what is that isothermal and adiabatic processes. I've already explained to you all. So quickly I'll tell you what was isothermal. Isothermal is the process where temperature is constant. You try to keep temperature same. So when you keep temperature same, change in temperature is zero. Whatever you take in the initial should be there till the final point in isothermal. You also know that it's a very slow process. Okay, whatever extra, whatever energy you give from outside, that goes everything in doing the work. The internal energy for isothermal is zero. Internal energy for isothermal process is zero. Then we had seen what is adiabatic. Adiabatic processes where there is no perfectly insulating. This is perfectly conducting. Here what we do, adiabatic means we insulate it. So here we have insulated walls. So no heat is exchanged to the environment or no heat from environment comes inside. So zero heat transfer. So that's why delta Q is zero. The rest everything will change over here. Okay, so these are the, so this is a very fast process. So this is about isothermal, difference between isothermal and adiabatic process. So we'll try to study about this Carnot cycle. The first step, what he does is he takes this piston, the whole system, and he keeps it on one source. Source means I used to normally put a fire like this symbol. So there's some external. So over here we'll take this as T1, which is a source of heat. This the block which is down. What we are assuming, this wall is perfectly conducting. Then he places infinitely small weights on this, small weights. So what is happening? There's idle gas inside. Now there is some source of heat. Heat is being supplied, okay? Perfectly conducting means it heat is going towards the gas. Gas is absorbing the heat. Now, okay, this first one, what he is trying to do is slowly remove one by one weight. Now small weight he removes. Okay, it's a small, extremely small weight. Now the weight has removed means what happens? Now the piston has to go up. So this, what will the gas try to do? It will try to push the piston up. So trying to push the piston up means the gas is trying to do the work on the piston. It's trying to push it upward because one small weight is gone. So from where does this gas get the energy from? He is using the energy from this source of heat. Temperature is not changing. Whatever energy it is getting is utilized to do the work, not to increase the temperature. If this was at 20, it will remain at 20 only throughout, because this heat is not increasing the temperature of the gas. Why? Because the whole heat is getting utilized to push the piston up. There is no extra energy for this one to rise. So what will happen is, slowly remove the weights. This is a slow process. So what is going to happen? The gas will expand. Now what happens? It has to do work. Takes energy from the source. Temperature of gas remains same. So what is this called? When temperature of the gas remains same, that is called as a isothermal. So gas is expanding, so it is called as isothermal expansion. Because whenever the temperature of gas remains same, we know that it is called isothermal expansion. Because it's a slow process. Slowly are removing the weights. So what is going to happen? Pressure will change, volume will change, but temperature will remain the same. Same temperature. Only pressure and volume changes in isothermal process. So this is step 1. That graph I'll just explain to you now. Then finally we will draw the graph one by one. I'll write. So now how it will look now? We have started. Suppose at this A, it will go till here B. So if it had started, you don't draw this now. Just only write this much and keep. Last final you draw the cycle. Or you want one part by one part, you can write for this one and keep, and then we'll draw the final one again. No, sorry, this is T1 only. Temperature will not change. Pressure and volume only will change once the gas expands. So remember, step 1 of Carnot cycle is isothermal expansion, where temperature remains the same. Pressure and volume only changes. So how much of this temperature is being supplied, or this heat is being supplied? Q1. Consider heat, the amount of heat energy supplied by this source is Q1. So AB is an isothermal process as per the diagram. We know that for isothermal process, change in temperature is 0 and internal energy is also 0. Now, as per first law of thermodynamics, we know that total heat supplied is work plus internal energy. This is first law of thermodynamics. Total energy is nothing but work plus internal energy. Total heat supplied. So what is the total heat supplied here? Q1. Work done. This is 0. So since we are using many different processes, no, I'll use this as W1 for first process, for step 1. So process 1, I'll just use this as W1. We have already derived a formula for work done for a adiabatic, for a isothermal expansion. You can just go back and refer. So as per that work done formula, we have derived this. This is the work done formula. So mark this as equation 1. This is the work done for isothermal process. I'll use T1 here because it's the first process. Now we'll see step number 2. For step 2, what Carnot does is he keeps that same system, whatever. Whatever weight, he keeps it on one stand. Here he uses perfectly insulated walls. No heat supplied outside, no heat supplied inside. The stand, whatever, like if there no source, the stand is perfectly insulating. It doesn't allow any energy from the gas to go out, or from everything is insulated in the second step. So insulating means cannot give heat outside, nor heat can go inside. So what he does is the walls are insulated. So no heat exchange takes place. So what he does is he starts removing all this weight very fast. So what is going to happen? Suddenly, if you remove all the weight, the gas will expand. But now this piston has to go up as these weights are removed. Now automatically it will not go up the piston. What it has to do now, the gas has to push. The stand, is it a source of energy? No, the stand is simply a stand. It doesn't have any, what is that? It's not supplying any heat like the first step. Now, from where will this gas get the energy from? There's idle gas anyways inside. So removes all weights. Gas expands. So for expanding, okay, for it to do the work, no external source is there. Because heat cannot come from outside. So from where is this energy going to be there? So it's like, consider an example, like you want to do an exercise or some running. So there are two options. One, you drink lot of glucose water or eat some food and then start running. So what is going to happen? Your body is going to utilize whatever you eat. So it's like whatever you're giving from external, that energy it will use and make you help to run. So that was happening in the first case. But now the second case, there's no food only, but still you are running. So what your body is going to do, it will start using your internal energy, which is already stored in the form of fats, okay, or some calories which are already there. It will start burning out your calories. So it's the same thing. which happens here. He has no source of energy to take out from somewhere else, okay, because they are insulated, no heat can come. So uses its internal energy to do the work. And when which is this process called, which utilizes the internal energy, that's called a adiabatic process. So step 2 is a adiabatic process. Your teachers might not explain this part, might just say that it's adiabatic, but easy to remember if you remember this process. What is important is to write this part. Main thing, uses the internal energy to do the work. So what is this again? Adiabatic process, or you can say adiabatic expansion. So the gas is expanding. Adiabatic, why? The word insulated is there. So for adiabatic expansion, you know that P1, V1, T1, sorry, now where are we at this point now? B. So P2, V2, T2 will move. All three things will change here. Only heat is not exchanged, but pressure, volume, temperature, everything will change here. T1, no? So we'll use this. This was T1, sorry. This will be T2. P2, V2, T1 will go to temperature also will change. Everything changes here. Only delta Q is 0, change in the heat supplied, or Q is 0, no heat is supplied. And work done for a adiabatic process. Okay. So if you want, as per thermal law of energy, you know that work, this is anyway 0. So work done is negative of internal energy. So we have again derived a formula for work done in an adiabatic process. We'll use the letter W2 for adiabatic process. This also formula we have derived, mu r T2 minus T1 upon 1 minus r. Mark this as equation 2. Now step 3. Step 3, what Carnot does is he places this on something, on a sink now. Earlier it was source, this is a sink, which is temperature T2. Same piston, same idle gas. Now right now the all weights were removed. Okay, then all the weights will be put here in step 3. Back. First the weights were removed. First they were slowly removed in step 1. Step 2, fast he removed. Now step 3, now he'll start putting them slowly back. Again, which one? This is perfectly conducting now, because there's a temperature has to flow. conducting, you know, conducting. Now what we'll do, slowly put weights. Now what is going to happen? Gas will compress now. So as the gas is getting compressed, it will release out the energy. Okay, so that is like the work done. Whenever you're compressing, it's like the work is done on the gas now. So whatever energy it is released, it will give it to the sink, because this will be at a lower temperature than this one. Okay, now what is going to happen in this process? The temperature of this gas is anyway not changing, because it's a slow process. In slow process, temperature does not change. You can say work is done on the gas now, because you're compressing the gas, the work is done on the gas. Temperature remains same. So perfectly conducting, temperature remains same. So it is called as a isothermal. Now gas is getting compressed, so it will called as a isothermal compression. So where were we? P3, V3, T2. I told you temperature will not change for a isothermal compression. Isothermal process, whether it is expansion or this, temperature never changes. Rest will change. So this will go to P4, V4. As for the graph, C to D is a same thing back, because Carnot says it is a reversible process. Temperature is same. Now same thing again for isothermal compression. What is going to happen now? Delta T, change in temperature is 0. Okay, so you know work done. So we'll use W3. Same let this now mu r, same as the first step, mu r T. Now 2 it is from here to here. Temperature T2. Now what are the volumes? We cannot use V2 upon V1 now. We'll have to use V4 upon V3, which is same as Q2 now. The heat exchange which takes place is Q2. For first process, we had used as Q1. Now this one is used as Q2. Because internal energy anyways will be 0. Exactly same like the first step only we have to write. Only thing we really have to use V4 and V3 now. In the last step, step number 4, again he'll place it back on the stand. So first step and the third step is same, because that is a cycle. This and this is same, and so that this and this will be adiabatic. So this is isothermal. expansion. This is isothermal compression. This will be adiabatic expansion. Same way we'll see the last one, adiabatic compression. Mark this as equation 3. Step 4, put it back on the stand. Again, insulating, insulated walls. It cannot go out. All the weights have been put. There's idle gas inside. In step 4, what you will do is you'll put the weights very fast. So what happens? Gas compresses very quickly. So what is going to happen? Work done on gas. But now what is happening? If there is work done means there is a release of the energy. The more it gets compressed, the molecules of the gas will start releasing out the heat because work is done on the gas. But heat cannot go out. Why? Because it is insulated. So that's why temperature will rise. So it's a fast process. Okay, no heat exchange. Outside it is not going. So therefore it's a adiabatic compression. Everything will change now. Even the temperature is changing. So P4 means what it is assuming now? As per this Carnot, it's a reverse process. So it will be back to its original term for them. That will be P1, P1 and P. So it's a full cycle. First expansion, this isothermal, then adiabatic expansion, then isothermal compression, and then adiabatic compression. So this is a Carnot cycle. We can draw now. So D to A is adiabatic compression. Again, you know that Q is 0, then no heat. We'll use work done now, like W4 mu R. Now this will be what? T1 minus T2 will have to use. Because from here it was T2 minus T1. Okay, final temperature minus initial. From T2 it went to T1. So T1 is considered to be a higher temperature because temperature will rise from T2 to T1. upon, what was that? 1 minus R. If you notice, if you want, you can just exchange also and keep, then minus will come out, which is same as minus mu R T2 minus T1 upon 1 minus R. Minus, if you take out, the terms will, so mark this as equation 4. So this is work done for all the 4 processes. The main thing what you should be able to explain is what is A to B, the isothermal expansion, what is happening, and it's work done equation. Same thing here to here. Even if you don't explain this, it is fine. Only the main part, this part at least should be known. The cycle, looking at this, you should be able to explain. All the 4 equations, what we'll do, what is total work done? Net work. Yeah, net means the total. All the addition of all the 4 works. Put all the formulae, equation 1, 2, 3, 4, all the answers you put. So W1 was W2 was W3 was this is mu r. This and this term will cancel. W2 and W4 will cancel because one is plus, the other one is minus. So total I'll take out mu r T1 common. Oh, that is T2, no? Just correct this one. Even in equation 3, by mistake, if I written as T1 only, just check. This is T2. So mu r is common. Only mu and r is common. So this is a total work done for a Carnot's engine. Now what we are doing is we are trying to derive the uh, efficiency of Carnot's engine. Efficiency formula I've already given to you all before also. Nothing but total work done. Okay, work done upon heat supplied. What was the initial heat supplied? The total work done upon Q1. This was the heat supplied to the system starting only. The only heat which was supplied was Q1. Rest, the only source we see in the diagram. What was the source of heat? We named as Q1. So W net, just substitute mu r T1 ln of V2 V1 upon V2. Sorry, V2 upon V1. And this also is V3 upon V2. Now let's just copying. Not even V3, it should be V4. Just check the, because this is the 4, this is 3, correct. This will be 2, 1, this is 4, and this is 3. For first step, it is V2 upon V1. And third step was volume was changing from 3 to 4. Just correct this, huh? Now I'll just take the value. What is W net? Mu R V1 ln of V2 upon V1 plus T2 ln of V4 upon V3 upon. Now the heat supplied, just look at the equation 1, it is same as W1. Just look from equation 1, W1 is same as Q1. So you can put that same value back. Q1 is same as W1. What is going to cancel? Mu and R. So I'll just distribute this term to both the term. Everything will cancel here. This is 1. Okay, 1 plus this is T1. This is the efficiency in terms of temperature. If I want, I'm just exchanging this, okay? Suppose anytime I'm interchanging the values, no? Log of A upon B is same as log of minus B upon A. Why I'm doing this, you'll understand later. We will need what is the value of V3 upon V4. So that's why I will just interchange this. So if I'm interchanging this, the sign will become minus. So mark this as equation 5. Next, all the processes we will see. First one was isothermal. What had happened? P1, only in terms of pressures we'll see. P1 V1 became P2 V2. Second one, for adiabatic, as per the formula, we always use this letter R. You can go back and check for the adiabatic process. Third one, again it was isothermal compression. So from P3 V3 we came to P4 V4. Fourth one was, this was expansion. This was compression. What happened? From P4 V4 we came back to P1 V1. Only for adiabatic we have to refer this letter R for the volume. What we'll do is we'll multiply all this. My aim is to find what is the relation between these volumes. So what I'm going to do, multiply all of them. Means all the left hand side will get multiplied to each other. All the right hand side will get multiplied to each other. So P1, V1, P2, V2, P3, V3, P4, V4 is equals to this was R now, and this is also R. P2, V2, all the right hand side I multiplied, all the left hand side I multiplied. First into second into third into fourth. Then right hand side first into second, third into fourth. Now whatever are the same terms will get cancelled. P1 will cancel, P1 will cancel, P2 will cancel, again P3 will cancel, and P4 will cancel. All the pressures will cancel because they have the same power. What remains is V1, this is what will remain after the pressures cancel out. The R powers will keep there only. Whichever R powers are there, no? Who is this one's partner? V2's partner is this one. So we'll bring him this side. R terms will keep there. So V4's partner is here. So we'll bring him here. This one, V2 is this, V3 is here. So V3 will take this side, V1 will take that side. So they're all multiplication. If you're taking it on the other side, they will become division. So V2 I'm bringing here. So it will go here. Then same way V4, V3 and V1 I'm keeping here. This one partner will come this side. Sorry, V3 and V1 will come here. Put it like this also. No. Okay, every corresponding values I brought together. No, just take the numerator on top. So this will be P2 R minus 1 because this is like 1. Same way 1 up, so minus 1. P4 raised to 1. If it takes up 1 power less, because we know that m, and if you have the same thing in n, then it is a raised to m minus n. Powers will get minus if it's division. Same way powers are same, so we'll make it common. As per mathematic rule, we know that if powers are same, then they always cancel out, and then a is equals to b. So this basically will cancel out. It's like how a square and you have b square. Then what you do normally, square is square root. You take square root on both the sides, then what would happen? A would be equals to b. Same way, any other power also, powers always cancel out. So as per that now, V2 is V3 upon V1. So we know that V4 upon V1 is equals to V3 upon V2. Mark this as equation 6. So what is V3 upon V2? Same as V4 upon V1. So final step, put with this in equation 5. Write it here. Put equation 6 in equation 5. What was equation 5? I'll just write it again. V3 upon V4. Wait, we'll just, this we have to arrange, no? Wait 1 second. What I want V3 upon V4, just correct this one. V4 you take on the other side. Accordingly you arrange, okay? What I want V3 and V4, no, together. V4 you bring down, so V2 upon V1. This you mark as equation 6. Whatever I need here, no, just look at the equation 5 and arrange this in the same way. What I want V3 upon V4, which is same as V2 upon V1. Now these two are same. So instead of V4 upon V3 upon V4, I can put it as V2 upon V1. So this will cancel because both are same. We have just shown it in equation 6. So final answer, efficiency of Carnot's engine is T2 minus. So this is finished with Carnot's engine. So all the 4 processes. First is adiabatic, this isothermal expansion, adiabatic expansion, then isothermal compression, adiabatic compression. Just try to know the graph. Theory wise, the chapter is over. Just 4 problems are there. Solve them. First one, 1 gram of water at 100 degrees Celsius is converted into steam at same temperature. If volume of steam is 1671 centimeter cube, find change in internal energy of the system. Okay, in thermal properties of matter, I explained to you all what is latent heat and what is specific heat, when to use. I had explained with the whole graph. See, whenever the water is boiling or whenever the water is freezing, sometimes there's a change of state. So whenever change of state is there, from ice to water or maybe from water to steam, we have to use latent heat. So that latent heat is given as UML, where L is your latent heat. And suppose if you have rise in temperature, if the temperature is rising from 0 to something, if there's a rise in temperature, change of state means ice to water or water to steam. These are called change of state. And rise in temperature means if the temperature is changing from 2 to 10 or whatever. Rise or change in temperature. Then you have to use this formula. They use either dq also you can use or q. mc delta T, where C is the specific heat. This type of problems are done in the previous chapter. So now what is happening? This is converted from water is converted into steam. So obviously there's a change of what is that? State. Temperature will not change. Till the every drop of water converts into steam, the temperature will remain as 100 only. So which there's a water to steam. So which formula for heat we'll have to use? Latent heat formula. If they are told the temperature is changing from 80 to 100, then we'll have to use this formula for heat. We'll write the data. Mass is 1 gram in terms of kg, then it will be 10 raised to minus 3 kg. Temperature is 100 degrees Celsius. Volume 1671 centimeter cube. But centimeter means 10 raised to minus 2 meters. Latent heat is given on, just write on. Latent heat of steam is 2256. And one given also, just try this, given 1 atmospheric pressure equals to 1.013 into 10 raised to 5 Newton per meter square. One atmospheric pressure, if you want to always convert it into Newton per meter square, then that is the relation. Sometimes even if you take 10 raised to 5, it's okay because this is ignored. So 1.03 is assumed to be 1 into 10 raised to 5, which is 10 raised to 5. So all this is given. Now we have to calculate the internal energy of the system. So the formula which we know from first law of thermodynamics is delta Q is CQ is delta. Whether you use D or delta, it's the same. It's nothing but the change in both. Some places you might not have this also. That's okay. But in this U and W letter should be there for sure. But now work is directly not given. So in terms of pressure also we know the formula. This is P delta V or P dV we have seen. You can use these letters also like this. Means the same. P, don't get confused. This also same, this also same. pressure into volume. This formula I've given under first law of thermodynamics. You can go back and check. Now, which this heat I will use now formula. I have two options. One is to use the specific heat formula or the latent heat formula. Since it is change of state, I'll have to use it, that latent heat one, that is m into L. dq is m into L. This we have to calculate. And now substitute. Okay, this dV also, I'll tell you what it means. Change in the volume. Obviously, now water is getting converted into steam. The volume will not remain the same as the every little bit of water drops are going into steam, its volume will decrease. So, whose volume will increase? Volume of the steam will increase as it goes on. So that will be volume of steam minus volume of water at the end of the process. Now, whatever is given is the volume of the steam. So, you can put the letter S here. Volume of steam. dV means change in the volume. Now, here we'll calculate what is the volume of water. Volume of water would be, it is given in terms of 1 gram of water. So, density is mass upon volume. Density is mass upon volume. Mass is 1 gram, so that is 10 raised to minus 3 kg. Volume I have to calculate, density will come here. Density of water will be 10 raised to 3. Always it's fixed, density of water. So 10 raised to minus 6 it will be volume. Volume of water will be 10 raised to minus 6. Now you just substitute everything. Mass is 10 raised to minus 3. Latent heat is 1671 into 10 raised to minus 6. du we have to calculate. Pressure. Where is the pressure here? 1.013 into 10 raised to 5. Volume of the steam is latent heat is here, 2 is 2256. This is the latent heat L, and volume is 1671 into 10 raised to minus 6 minus 10 raised to minus 6. Ten raised to minus 6 you can take out common. So what remains inside is 1671 minus 1. 10 raised to minus 6 means 10 raised to minus 1 into 1670 it will be. Two into 10 raised to minus 3 means 3 decimal shift. Zero, 1 decimal shift. You don't want to include this, you can just take it as 0.01. But this will be 1 now. Wait 1 second. 0.1 you can take. And then calculate. So that will be your internal energy. Answer will be in terms of joules. Whatever answer you get, write in terms of joules. Second question. Calculate change in internal energy of a block of copper of mass 200 grams when it is heated from 25 degrees Celsius to 75 degrees Celsius. Specific heat of copper is 0.1 calories per gram per degree Celsius. Specific heat of copper is this. Assume volume as negligible. Now this everything is in terms of calories. Suppose if it is in terms of calories, no need to convert this in terms of kgs. Last you can convert in terms of joules, which I will tell you. In the previous one, if you see, latent heat was given in terms of joules. That was standard unit system. So we have to convert everything in terms of standard units, mass into from grams into kgs. Calories is a CGS system where it includes grams only. You can keep that as 200 only now. So mass is 200 grams. Specific heat of copper C is given as calories per whatever gram. Temperature delta change in temperature. Volume to be taken negligible means delta V or dV you have to take as 0. So directly you have to calculate the internal energy. Same formula, dq will be du ed. Now dq, which one we will use now? Now there's a rise in temperature. Rise in temperature formula. Here we cannot use ml. Here we have to use mc delta T formula. Anyways, volume is 0, so that would be 0. I just substitute. Mass is 200 grams. C is 0.1 calories. Change in temperature is 50 degrees. So if we calculate 200 into 5, it will become 1000 calories is, but we have to write it in terms of joules. So joules to calorie conversion, you have to multiply it by 4.2 because 1 calorie is 4.2 joules. So 4000 that's the answer. Question 3. Calculate change in internal energy when 5 grams of air is heated from 0 degree to 4 degrees Celsius. The specific heat of air at constant volume is 0.172 calories. Again, this is given in terms of calories. The specific heat C is 0.172. Mass we can take in terms of grams only now because everything is CGS. Temperature changes 0 to 4 degrees. So 4 degree minus 0 degree. Now constant volume it has been said. So whenever we have constant volume, always delta V is, or dV is 0. Change in the volume is 0. Same like the previous formula only. Same formula we'll have to use. Exactly same thing. Because there is a rise in temperature, same formula. Mass is 5. C is 0.172. This is 4 degree. Du we have to calculate. This is 0. So this everything what you are getting is in terms of calories. For this is calories. Okay. I want to convert it into joules. Then I have to multiply whatever is with 4.2 joules. And after multiplying it with 4.2, we'll get it as 14.4 joules. That's a change in the internal energy. Du means change in internal energy. And the last problem. A volume of 10 meter cube of liquid is supplied with 100 kilocalories of heat and expands at constant pressure of 10 atmospheric pressure to final volume of 10.2 meter cube. Calculate work done and the change in internal energy. A volume of 10 meter cube of liquid is supplied with 10 kilocalories of heat and expands at constant pressure. Pressure is given as 10. So final volume. Now directly heat has been given. Change in the volume. Now volume is not constant, so dV will not be 0. So V2 minus V1. So how much will it be? 10.2 minus 10. So that will be 0.2. Now you have to be careful here. Pressure is constant, which is given as 10 atmospheric pressure. We have to always convert it into Newton per meter square. That is basically Pascal. 10. So I told you, either you can use that direct, this one, 1.013 into 10 raised to 5, or straight away it will make hardly any difference because 1.0, if they have not given exactly in the problem, you can just assume it to be 10 raised to 5. But if they mentioned in the question, then you can take. It was not there in the question. If not there, then you know that 1 atmospheric pressure is always equals to 10 raised to 5 Newton per meter. I just take the formula and substitute. Hundred kilo means 100 into 10 raised to 3. Kilo means into 10 raised to 3. Du. Okay, so du we have to calculate. So this is PdV, huh? Plus pressure is how much? 10 into 10 raised to 5 dV. dV is how much? That same thing, 10.2 minus 10. Now here we have to be careful. This is given in terms of calories. And if you see, this volume is given in terms of meter cube. Meter cube is what? SI system, it is joules. So either you convert this into joules or this into calories. But since this is in calories, what we can do is just try to, whichever way, the calories you can convert it into joules. So 100, or this the other way around, divide by 4.2, however you want. But answer will be in terms of calories then. So this will can convert 4.2 joules. Same thing, 0.2, and then you calculate. This is plus. So this will anyways give me 10 raised to 6. Bring this on one side. Take out 10 raised to 6 common. Four into 10 raised to 6 joules will be the answer. So I'll stop here. Any problems